This is an add-on lecture to introduce 5th generation mobile communication technology. Now, 5th generation mobile communication technology is still in its initial stage of being standardized. So this is not a reality technology yet. But I added this lecture to the course because I feel that you need to know what's going to happen in the future. What are the set goals? What is the vision? And by this, I want you to study, develop new technology, and add on to what will become 5th generation mobile communication systems. Join me and let's work together on it. So now I'll introduce what is 5th generation mobile communication technology. And I will talk about the 5G vision, which deals with service, technology, and standards, and then key enabling technologies, as you see here. Among that, we have advanced network technology, millimeter wave, multi-RAT, which is radio access technology, advanced MIMO, which is multiple input, multiple output. In some cases, you can call it advanced MIMO. If you actually both use both, MIMO or MIMO. It's based on preference. In addition, we have multiple access techniques and advanced D2D, device-to-device technology, and small cell technology. Now, to take a look at the service vision, you can see something like this. Some of the major big objectives are everything on cloud. We want to support telepresence through 5G technology. We want to support immersive experiences in various ways through 5G technology. In addition, to support a lot of different devices, IoT, Internet of Things connections, as well as so many more wearable computing, electronic smart devices, as well as our smartphones. In addition, augmented reality supported devices such as head-mounted display, glasses, or other type of augmented reality displays. Well, there's going to be tremendous amounts of massive connectivity. We want all of this to be sufficiently supported by 5G. So therefore, 5G's vision combines the following: cloud services, extremely high-speed internet, wireless HD CCTV, personal broadcasting capability, location-based technologies, and wireless backhaul technology. The 5G target performance can be set with these objectives: a data rate where 10 gigabits per second or more is supported in the cellular area. In addition, 1 gigabits per second even at the cell edge, which is a location where the performance is worst. The spectral efficiency, we want to boost it up. We want to accomplish 10 bits per second per hertz. So in other words, if you're given, let's say like a certain amount of bandwidth, then you can see an approximated data rate of how much you should get using the new high spectral efficiency modulation techniques. In addition, considering vehicles, Internet of Things, smart devices, wearable devices, smartphones, and so much more, within a square 1 kilometer area, we want to be able to support 1 million devices. A tremendous amount of connectivity that's being supported is one of the objectives. In addition, very, very high mobility and very small latency. For example, we want to be able to support vehicles, trains, or other aircrafts that move at 300 to 500 kilometers per hour. In addition, for end-to-end service, from the moment you hit your request data button, the data is delivered to you within 5 milliseconds. We want 5 milliseconds technology. And when you just look at how long it took to get over the access point to the device or the base station to the device, we want that to be less than 1 millisecond. In order to accomplish this, what do we need to do? Here's how it goes. First, the 5G timeline and key technology based upon the 5G standardization plans. As you can see, the standards are based upon the ITU, the International Telecommunication Union. And as you see in this time chart, you can see the time of 2015, 16, 2017, 2018, 2019, and we're hoping that all becomes a reality by 2020. The release standards that are being prepared are Release 13, Release 14, Release 15, and we come to release 16, which helps us get into further enhancements and ready for the products. The core technologies that must be developed are above the 6 gigahertz frequency system, RFIC, and antenna technology. We also need new waveform designs. In addition, multi-radio access technology, multi-RAT internetworking technology. For below 6 gigahertz signals, we want to accomplish massive MIMO technology. In addition, we want advanced device-to-device, advanced D2D technology, and also enhanced flat network technology. You may be thinking, enhanced flat network? What does that mean? Just wait, I'll explain it to you. Now, 5G enabling key technologies. This is a list, and let's see where we can go with these technologies. First, advanced networking technology. Now, I said flat and distributed network architecture. We want an integrated and distributed network function. We want it to be programmable. We want it to be a programmable network architecture that uses SDN, software-defined network, and NFV, network functions virtualization. And you may be thinking, why do we want that? What was a problem that we had in 4G technology? I'll explain it to you. Now let's take a look at software-defined network, SDN. SDN decouples the network control and data forwarding paths and functions. Distributed management by using the shortest data path without traversing the core network is what we would like to accomplish. Now, network control can be directly programmable, and this flexibility provides us with so many enhanced features. The underlying infrastructure is abstracted for applications and network services. NFV, Network Functions Virtualization. NFV is a technology used to virtualize complex hardware-based network node functions into software building blocks that can be combined and chained to create advanced communication services. So in other words, what used to be in one system block, we look at those functions, we take them design these into building blocks in software, just like Lego pieces of a puzzle or a Lego combination small plastic infrastructure, and we combine them based upon how we want to use them. Now, these components are what we're looking at in NFV. NFV eliminates dependency on complex hardware-based nodes by using flexible software blocks that are called VNFs, Virtualized Network Functions. It provides improved flexibility and improved functionality and improved efficiency. Now, I'm going to compare 4G, the LTE network, to 5G. And I'm going to briefly talk about 4G LTE architecture again. I already have this in my former lecture that exists on 4G LTE, but this is just a short overview, so I can make the comparison of how 5G is making progress over existing 4G technologies. Now, the 4G LTE architecture, a quick overview. Here we go. The LTE network has a hierarchical core network architecture, as you see over there. It has the overall system that's connected to the internet is what we call the EPS, the Evolved Packet System. Among that divides into two components. One component is the EPC, which is the top part, and you can see those green blocks up there. Those are the core components that form the Evolved Packet Core. That's the core network. Below, there's the EUTRAN, which is the Evolved Universal Terrestrial Radio Access Network. That's where the E node B, the base stations, are connected through, and they provide access, mobile wireless access to our smartphones and our other type of phones that we have that are mobile devices. Now, this architecture, all terminal traffic is tunneled through centralized nodes, such as like the serving gateway or the PDN gateway that we have up there. And these controls are connected through the support of the MME, HSS, and PCRF modules. Now, high end-to-end latency, high backhauling load, low reliability are some of the results that could come when these networks are overloaded with too many users. Now, some of the blocks were the PDN gateway, the P gateway, which provides these functionalities. Then we have the serving gateway, which provides packet routing and forwarding, mobility anchor for inter-eNodeB handover. Now, but when you go into more advanced handover, basically the IP address allocation to the UE, and also mobility anchor for non-3GPP handover, combined between 3GPP and non-3GPP handover, that's what the PDN gateway supports. The other components within the LTE 4G network are the MME, Mobility Management Entity, which supports mobile roaming, user authentication, and controls the process of the signaling between the UE, the user equipment, and the evolved packet core. Then there's the HSS, Home Subscriber Server. It's a database containing the user's subscription information. And then the PCRF, Policy Control and Charging Rules function. Now, in advanced network, what we wanted to have is a flat distributed network architecture. Distributed management, providing the shortest data path without traversing the core network, is what we want. So we want these features, and in addition, we want context-aware resource allocation considering real-time traffic, service type, and device characteristics. Popularity-based content caching using content delivery network techniques for latency and packet traffic reduction. And as you can see, CDN technology that I mentioned before, it's going to be used over here. Now, one of the things that I said before, as a target, we want to have less than 5 milliseconds of end-to-end latency, which means that on my smartphone, when I request for contents, a certain information, I want it to be delivered to me within less than 5 milliseconds. In order for that to happen, the contents must be predicted and brought to somewhere close so that as soon as I ask for it, it's delivered to me. That is supported by CDN technology. Now, we have millimeter wave systems. There is huge bandwidth available at these high millimeter wave frequencies, which are above 6 gigahertz. And compared to the current LTE band, we can gain so much more capacity. For example, here, 2.2 gigabits per second of a data rate can be supported by the 28 gigahertz band using multi-cell and a 500 megahertz bandwidth transmission technology. In order to make this possible, we need supporting technologies such as 28 gigahertz polarization, interleaved array, antenna techniques. In addition, we could use like 60 gigahertz, 360-degree covering, 16-chain CMOS RFIC techniques. So above the 6 gigahertz range, look at some of the frequency regions that are of interest, such as the 28 gigahertz, the 39 gigahertz, and over there using a combination of Wi-Fi based upon the 60 gigahertz range, such as 802.11ad or WiGig. Now, these regions are going to be used by Wi-Fi, but 5G technology is focused on using both these heterogeneous radio access technologies to combine all forces together to achieve extremely high data rates. So the 60 gigahertz Wi-Fi techniques will also be pulled in to the range of servicing 5G technology. In addition, way over there, you have the 70 gigahertz 5G devices. Then comes the multi-rat internetworking techniques based upon combining former technology, which was the other Wi-Fi, and the former 4G and 3G technique frequency bands, which are shown at the bottom. The focus here is for our user equipment UE, network-based multi-rat, multi-radio access technology, coordination technology to pull in former resources and resources that we have from other frequency and transmission techniques. We want throughput and connection reliability enhancement using unlicensed and licensed spectrum coordination. We want internetworking and integrating with the 5G system and with other radio access technologies, such as the 3G, 4G, Wi-Fi, Bluetooth, and other techniques as well. Now, advanced MIMO, or advanced MIMO. Now, data rate enhancements using full dimensional MIMO is one focus. In addition, spectral efficiency enhancement using multi-user MIMO, energy efficient and data rate enhancements using virtual MIMO techniques, and COMP, coordinated multi-point MIMO supported techniques. Now, in my 4G LTE lectures, we already studied COMP, but I'm going to briefly review them. Here, coordinated multi-point COMP technique, this improves the coverage of high data rate, cell edge throughput, and system throughput. COMP coordinates multiple eNode Bs to communicate with the user equipment. We want to increase throughput by reducing inter-cell interference, and this is accomplished using the COMP technologies down here, where we have CS, CB, JT, and DPS. CS stands for coordinated scheduling, CB stands for coordinated beamforming, JT stands for joint transmission, and DPS stands for dynamic point selection. For more details on this, please go to my 4G mobile communication lectures on LTE. And then we have multiple access. Now, multipath transmission technology enables a device to use multiple transmission protocols, such as our cellular 3G, 4G, wireless LAN, like Wi-Fi, and Bluetooth techniques at the same time. Now, multipath transmission enhances connection, reliability, and data transmission rates. So in other words, we can get higher data rates and have them much more stable and reliable. So it's like a win-win, getting everything better together. Now, MPTCP, which is multipath TCP, this enables a device to configure multiple TCP sessions over multiple wireless links. So in other words, if you have your smart device and you're using it, you make one connection through Wi-Fi and make another connection on LTE to the LTE base station eNode B. And then you use these two links together to support the data that is provided to your smart device. This is what techniques like MPTCP or like SCTP, these techniques can use. And they enhance the technique such that it's more reliable and also you have higher data rates. This is the beauty of multipath techniques and also multiple access techniques working together. The advantages of multiple access are throughput maximization based on path capacity enhancement and channel error reduction. In addition, we can accomplish mobility improvement and latency reduction using improved path switching control. In addition, we can reduce the handover interruption time, the HIT, using RTO, retransmission timeout control, and improved device and user equipment UE-based handover decisions. Next, we look into advanced device-to-device communication. This is most effective in offloading data from the mobile network such that the load and cost of processing data and signaling is reduced on the mobile network. It's wonderful. So if we can allow devices to communicate with each other, then the amount of traffic that needs to be supported on the mobile radio access network and the overall core network can be reduced tremendously. And that's very, very good. In addition, D2D technology can support MCPTT, Mission Critical Push-to-Talk. In addition, it can support V2X communication, where V is for vehicle and X can be anything. In other words, the X can be another V as vehicle to vehicle, or it could be vehicle to pedestrian as V2P, or it could be vehicle to infrastructure, such as V2I, where the infrastructure is a traffic roadside unit. This is based upon the IEEE 802.11p and the IEEE 16.09 protocol, and providing cooperative computation techniques supporting ITS, Intelligent Transportation Systems. Efficient exchange of emergency signals between vehicles and roadside units is what can also be accomplished and provide various good support systems for traffic support units. Next is small cell technology. Large number of small cells in a given area can provide significant throughput enhancements, And that's what small cell technology is trying to provide. A distributed and self-configured network technology is needed, and this will enable easy to deploy small cells. And that's the focus of small cell technology in 5G, where various techniques to manage heterogeneous networks such as IC-IC, CA, HETNET, COMP, and SON, these techniques can be used. These are the techniques that I introduced in 4G, which is the LTE lectures, and I recommend for you to visit that lecture to review these components. And as you can see, the 5G performance goals and how these goals are going to be accomplished was introduced. Comparing these techniques over there in that chart, you can see how these target specs are met based upon comparing techniques. Over there, as you can see, IMT 2000, that's our 3G technology. On top in green is the IMT Advanced. That's the 4G technology. And our ultimate goal of what we want to accomplish by 2020 is the red. It's over there, which is the 5G technology. These are the references that I used, and I hope that they will be helpful to you. Thank you.